Hello, and welcome to another lecture in the course. Today we're going to look at these quick sections, subsections 611 and 612, on convergence of subsequences of functions and equicontinuity. We're really looking towards proving Arzelà-Ascoli theorem and Montel's theorem. Really, Montel's theorem is what we're interested in. On existence of convergent subsequences. So the book you can get at the link in the description for free. All right, so what's the goal? So the goal, and we're not going to get to this goal in this lecture, the goal is to classify the relatively compact subsets of the space of holomorphic functions. Really, we're trying to figure out when do we get that given a sequence, when can we find a convergent subsequence? So something like Bolzano-Weierstrass. That's really, the kind of term that we'd really like. Bolzano-Weierstrass works. I mean, it works more than just in C. It works in Rn, but basically this idea that suppose that I have a bounded sequence in C, then there is a convergent subsequence, and we've used this before. Right? Something like that, something along those lines. But of course, this is for numbers. So we're not going to get anything like that for functions. We're going to get something like that for holomorphic functions, but with a little bit more, you have to be a little bit more careful. So here's some examples for, like, if you have just, any old functions, not necessarily holomorphic. So let's suppose that sine nx when n is the integer, right? Where we are in the sequence, and it's just we're thinking of it as just a function of the real variable x, right? So this sequence of functions doesn't actually converge to anything in any reasonable way. I mean, at some points, like for example at 0, right? Because when I plug in x equals 0, the n doesn't really matter. We always get 0. So yeah, I mean, it converges there. But actually on no interval does it converge pointwise, right? I mean, there might be some points where it converges, but it's, like it doesn't converge on all points of an interval. So the proof is not too terrible. It requires some measure theory, or at least the proof that I know of. But right, you cannot expect something like Bolzano-Weierstrass is the point, right? For functions, just without wanting something like holomorphic or some extra conditions. And this is not even for pointwise, so not even for like the simplest of convergences, right? And these are all bounded, right? All bounded by 1, right? So cannot expect something this simple. There has to be some other hypothesis that we need, right? All right. Now another example, one that actually does converge. So let's look at x to the n, and let's just look on this unit interval 0, 1, the closed interval. Now that's a wonderful sequence. It converges pointwise, but it converges to something that's discontinuous, right? It converges to 0 everywhere except 1, and at 1 it's just always 1, so it converges to 1, right? So it doesn't converge in the same class of functions, even though it converges, right? So these are sort of the type of issues that we want to deal with, right? I mean, if we're we're going to want to start with some sequence of holomorphic functions. We're going to want to have some sort of boundedness on them. So let's even just say bounded. What sort of convergence do we get? And we'd really like the limit to be holomorphic, right? So, all right, and we've talked about convergence before. So, really. In this chapter, we're not worrying about the existence of a convergence sequence and the right sort of convergence, which, if you recall, is the uniform convergence on compact subsets. All right, so let's start with boundedness. What do we mean by bounded? And it's actually, we can be a little, especially if we're talking about pointwise, we can be a little less less strict with what do we mean by bounded. So sometimes it's useful to just say pointwise bounded. Now, pointwise bounded, we mean that it's the sequence, right, is bounded when we evaluate it at a point, right? So for any point in a sequence of functions, right? Here x is any set. There is some bound, right, that depends on the point, right? So pointwise bounded means that we have a bound, but it may depend on the point, right? It's uniform over the n, but it's not uniform over the x. Now, if we also have uniform over the x, right? If we have a single m that works for all x, we're going to say that it's uniformly bounded, right? So that means that you have one m and all the functions in the sequence are bounded by that m for all x and all n, right? All right. Now here's an example of kind of what sort of problems you might encounter. So this sequence of functions, these are all going to be bounded. So each particular one is going to be bounded. They're going to be sort of, they go to 0 at infinity, right? Notice that there's no power of 2 in the numerator. So the x squared in the denominator sort of wins out as x goes to plus infinity or minus infinity. These are all nice and bounded functions. And we're never dividing by 0. X is now just a real number. But and these are going to be pointwise bounded because it's actually, it goes to this sequence converges pointwise to 0, right? So pointwise, because pointwise we get convergent sequences, or they're clearly pointwise bounded. So we get pointwise bounded, but we do not get uniformly bounded, right? So they're bounded functions. It's a sequence that is pointwise bounded, but it's not uniformly bounded. So it's it's an exercise to prove that that's what happens. The best thing to do is to graph a bunch of these, and then you'll see why that's true. All right. Now, if our domain X is countable, then we actually can always find subsequences, right? And all we need is pointwise bounded, right? So suppose that we're given a countable domain and a sequence of pointwise bounded functions, then there exists a subsequence converging pointwise. All right. So, and it's basically the diagonalization argument. It's actually kind of a cool argument, right? So X is countable, so it's a sequence, right? So we might as well write it as a sequence. Now, so we're gonna basically go through the points in X, right? So first, this is pointwise bounded. So this sequence at x1, right? This sequence of numbers is bounded, right? So by Bolzano-Weierstrass, there exists a subsequence, right? Now we're going to write it slightly, slightly differently, just so that we don't get, we're going to take subsequences of subsequences of subsequences of subsequences. Writing that sort of the tower of subscripts would just be a mess. So we're going to write. We're taking the first subsequence, so we're going to put f sub 1 comma k, and k is now the index, right? And so we're going to say, well, that's the subsequence of this guy that converges at x1, right? So we've taken a subsequence of our sequence, and now we have a subsequence that converges at x1, right? And Now we keep doing this, right? So we're going to define the mth subsequence. So it's going to be a subsequence of the m minus 1th subsequence, right? So, we basically, if we have this subsequence, the mth subsequence of f of the m minus 1th subsequence, that makes the sequence converge at all, xj for all j less than m. So 1, 2, 3, 4, 5, all the way up to m. So basically, suppose that we have this defined up to m, right? We want to define what is going to be the new subsequence, the m plus 1th subsequence, right? And well, we basically do the same thing that we did for the first one, right? We let it be a subsequence, the m plus 1th is going to be a subsequence of the mth subsequence, such that this guy converges, right? So we get convergence at the x sub m plus 1, right? Now, because this was a subsequence of, it's a subsequence of the m subsequence, which is a subsequence of the m minus 1 subsequence, and so on. So, this actually converges not just at the x m plus 1, it converges at all the xj, because it's a subsequence of a subsequence that converged there, right? Like, it's, for example, it's a subsequence of this subsequence with the first one, right? And that converged at x1, so therefore this guy also converges at x1, right? And so it converges not just at the x m plus 1, it converges at all of them, right? All the j less than m plus 1, less than or equal to, right? All right, now, if x was finite, right? I mean, countable, right? Well, I mean, I guess I put in the infinity over here. So I was thinking infinite, right? But it could have been, countable could mean finite. Well, then we're done, because you just stop. If it has m element, then you just stop at m, right? And there's your subsequence. But, okay, so suppose that there isn't, a stopping point, right? There's an infinite countable set. Well, pick this subsequence, right? So basically, we're going to take the kth element in the subsequence is going to be the kth element in the kth subsequence, right? That's the diagonalization. And now, by m tail, I mean, I'm basically going to, cut off the first, I guess here, m minus 1 elements of the sequence, right? So if you look at the m tail, so if you start the sequence at m, right? Well, it's a subsequence of the mth sequence, right? Mth subsequence, right? So therefore, the f sub kk converges at x sub m because the f sub mk converge there, and it's really, we can ignore the first m elements. It doesn't really matter for convergence, right? I mean, it's only the tail that matters, right? So that means that this subsequence, this new subsequence, well, it converges at all the x m, right? For all m. All right, so that's done. So we know we have, we can always do this on countable sets, right? Now, of course, the problem is that, we're generally not going to be thinking about countable sets. I mean, even in the real case, let alone the complex case, we're thinking of, well, let's suppose the complex case. Let's suppose the case that we're really interested in is sequences of holomorphic functions. Well, they're defined on open subsets of the complex plane. So, that's an uncountable set, right? I mean, there is a countable dense set in there, right? But if you have a countable dense set, you need something more to get convergence, right? Because it's okay. So you have convergence at points that are arbitrarily close, but you need something that sort of ties it together to get convergence everywhere, right? We're really interested in continuous functions, I mean, if you remember, when we started talking about convergence of sequences, it's really the convergence for holomorphic functions is the same as convergence for continuous functions. So we're really interested in what makes continuous functions converge, right? So we want something that's going to make the function convergent, something that's going to make them converge to a continuous function, right? So we need a little bit more uniformity. We need some uniformity in the continuity. We don't just want a sequence of continuous functions. We want a sequence of functions that are continuous in some sort of uniform way. And that's where equicontinuity comes in, right? So suppose that we have a set of functions. So this S is a set of functions, right? Which are complex valued functions on X, and we're going to say this set is equicontinuous at X if, well, it's basically like the definition of continuity, right? If for every epsilon there is a delta, so that if Y is within delta of X, that you have that f of y is within epsilon of f of x. But now the difference is for all f in S, right? So you're supposed to get, right, given epsilon, supposed to get one delta that doesn't depend on the f, right? It can depend on the x, right? That's why it's equicontinuous at a point, but it's not supposed to depend on the f, right? And we're just going to say that S is equicontinuous. So if it's equicontinuous at all points, just like for continuity, basically the terminology is the same. So the only difference is, this for all f in S, right? That you're supposed to, get this to work for all functions equally. All right. Now, if we also get uniformity in the domain in X, then we're going to call it uniformly equicontinuous, right? So this is just like uniform continuity, except again, we add this for all f in S, right? So S is uniformly equicontinuous if, so not at some point, it's uniformly equicontinuous, so on X, right? On capital X, on this metric space. It's uniformly equicontinuous if for every epsilon there exists a delta, so delta only depends on epsilon, right? Such that if you have x and y, 2 points in this metric space that are within delta of each other, then f of x is within epsilon of f of y, and this is supposed to hold for all f in S, right? So now, basically, so uniformly equicontinuous means that the continuity is uniform, over both the domain and the functions, basically. All right. Now, for if S is a finite set, then it's a fairly easy to see exercise, maybe. Well, I mean, this is the same thing as continuity and uniform continuity. So a finite set of functions is they're all continuous at some point if they're, if the set is equicontinuous at that point. And similarly for uniformly continuous, a finite set of uniformly continuous functions is uniformly equicontinuous. But for infinite sets, that's no longer true, right? I mean, it's basically this you can, for finite set S, you can always find, if you have finitely many deltas, you can take the smallest one, right? But if you have infinitely many deltas, the smallest one could be 0. So or the infimum could be 0. So you no longer can just take the infimum of the deltas to get something positive. All right. Now, for compact sets, so if we start on a compact set, if the functions are defined in a compact set, as we would expect, as is true for single functions or finite set of functions, if I have a continuous function on a compact set, it is uniformly continuous. So similarly, if I have a compact set an equicontinuous set of functions on that compact set, it's actually uniformly equicontinuous, right? As one would expect. And the proof is actually basically the same idea, right? So, all right, so here is the proposition, right? Suppose that we have, an equicontinuous sequence of functions, then the sequence is uniformly equicontinuous, right? As long as X here is compact, right? So for compact sets, we automatically get this uniform equicontinuity, which is going to be useful. So, okay, so how do we prove it? Let's suppose it's not uniformly equicontinuous, right? The sequence is not uniformly equicontinuous. Now, what does that mean? That means, so you have to sort of unpack this negation, right? What does it mean to not be uniformly equicontinuous? That means that there has to exist an epsilon such that for every k, there is an index n sub k. So it's going to be it's basically that there exists a function in this sequence, right? Such that and 2 points x sub k and y sub k that are less than k. Oh, sorry, 1 over k within within each other, right? So the distance is less than 1 over k. So for each k, I get sort of closer and closer points, and the difference of the values is bigger than epsilon, right? So you cannot, right? It's basically this idea that you're going to be able to, or you're not going to be able to find this single delta, right? That the delta would have to go to 0. That's basically what we're getting. So this is exactly the negation of being uniformly equicontinuous, right? All right, now, because X is compact, right, we have Bolzano-Weierstrass, right? I mean, Bolzano-Weierstrass for metric spaces, right? But there is X is compact, so it's sequentially compact, meaning that every sequence has a convergent subsequence, right? So these sequences, the xk and yk, have convergent subsequences, right? So I might as well, because over here, right? I mean, if I throw out a bunch of these things, right? I have it still works, right? I mean, I make the distance even smaller, right? So I might as well just take subsequences, right? Now you have to be careful when taking a subsequence. You want to subsequence. So first take a subsequence such that xk converges, right? And now take the corresponding subsequence of yk. Now that one doesn't converge, but that's bounded. So now I take a subsequence of that subsequence to make sure that both the xk and the yk converges, right? And I will still get this property, right? For those subsequences. Well, so now if I have convergence, right, I can say that both of these subsequences, or both of these sequences, sorry, both of these sequences converge to some point in X, in capital X, right? Now, so for any delta, right, take a k such that, because both of these converge, so take a k such that the distance of x sub k is within delta of x and y sub k is within delta of x, right? Because these both converge there, we have such a k exists, right? Okay, so now, we also had this thing, right? So for that particular index n sub k, right, we get that the difference between fn sub k of xk and fn sub k of yk, that is bigger than or equal to epsilon, right? that's by definition of or by this assumption that this sequence was not uniformly equicontinuous, right? So now you do you do a little bit of estimation, right? You basically you add and subtract the fn sub k of x, right? And then you do triangle inequality, and you get that this sum over here is bigger than or equal to epsilon. Now, what does that mean? That means that at least one of these, right? At least one of these is bigger than or equal to epsilon over 2, right? Because, well, their sum is supposed to be bigger than epsilon, right? So therefore, f sub n is not equicontinuous at x, right? Because that's, it should be, right? We have this x and y, xk and yk, and those converge to x, but we can always, no matter how, what the delta is, we always find some xk or yk. I mean, that doesn't really matter which one you take, such that this thing or this thing, again, it doesn't really matter which one you take, they're both a point within delta of x, where that difference is bigger than epsilon over 2. So that cannot go to 0, right? So this is not equicontinuous at x, right? So that means that if fn is equicontinuous, right, then it is uniformly equicontinuous, as long as, of course, X was a compact metric space. All right, so maybe some exercises, useful exercises. So suppose that we have a compact metric space and a sequence of continuous functions that converge uniformly, then prove that it is uniformly equicontinuous, right? Which is really the thing that, because we're going to want convergence on compact subsets, right? So, restrictive a compact subset, right? And basically this says that it seems like the right notion that we're actually going to get basically the opposite, right? For, if we get also boundedness, right? But if it converges uniformly, then it's uniformly equicontinuous. And if you get boundedness, we're going to get a subsequence that converges uniformly on compact subsets, right? So it's the right notion, right? The equicontinuity is the right thing that we need, right? Or at least for the subsequence. But it's if the sequence is equicontinuous, the subsequence is going to be equicontinuous. But basically, to get uniform convergence, which is sort of the, because we're going to want uniform convergence on compact subsets, to get that equicontinuity is that sequence is going to be equicontinuous. So therefore, that makes sense to require it, because that's sort of the the weakest thing that we could hope, right? It has to be at least equicontinuous, and it turns out that's enough. So next exercise is so let's see how the derivative can come into play, because, well, in the end we're gonna get stuff that's differentiable. I mean, we're talking about continuous functions at this point, but eventually we're going to talk about holomorphic functions. Those are all differentiable, right? And basically it's something about boundedness of the derivatives, right? So here is a very simple example of that. So suppose that you have a sequence or set of functions where the derivative is uniformly bounded, right? Then prove that it's uniformly equicontinuous, right? So it's basically the derivative, right? If you remember, from when you learned about continuity and Lipschitz continuity, right? The Lipschitz constant is basically, so that's the thing that you can get from, like, if you have differentiable functions, if you have a bound on a derivative, it's the Lipschitz constant, right? That's basically what's happening here. All right, so so we're gonna sort of continue with this and actually prove the Arzelà-Ascoli theorem next time. So all right, so see you then.